One crushes entire stars like they're nothing more than cosmic dust. The other spins at nearly the speed of light, rotating over 700 times every single second, firing out powerful beams of radiation that can literally strip the atmosphere off planets. So, in a battle of the universe's most extreme objects, who wins? Today we're setting up the most intense, mind-bending cosmic showdown imaginable. It's not just any fight, this is the ultimate heavyweight championship of the universe. In this corner, weighing in at a staggering 4 billion solar masses, capable of swallowing planets, stars, and even light itself, the black hole ***. And in the other corner, a 20-kilometer-wide titan spinning like a cosmic blender and denser than anything you've ever imagined. ***, the neutron star ***. Get ready because we're diving into 5 epic rounds of interstellar madness, analyzing their physics, their terrifying power, and who would win if these two ever went toe-to-toe. Let the ultimate cosmic battle begin. Let's get ready to rumble. Round 1, Gravitational Pull. Who dominates the universe with their invisible grip? ***. Let's start with the black hole, a terrifying monster of gravity. It's got something called an event horizon, an invisible boundary that marks the point of no return. Once anything crosses that line, not even light can escape. You could shine the brightest flashlight ever made straight at it, and nothing would come back. That's because the gravity of a black hole is so overwhelming, so absolute, that it doesn't just attract things, it actually bends space and time around it. Imagine space like a giant rubber sheet. Now drop a bowling ball on that sheet. It curves, right? That curve is how gravity works. Now replace the bowling ball with a black hole. The sheet doesn't just bend, it rips open. That's what a black hole does to reality itself. But don't underestimate neutron stars. They may be smaller, but their density is absolutely insane. Just one sugar cube's worth of neutron star material would weigh around 4 billion tons. That's right, Mount Everest squashed into something the size of a dice. It's an object so tightly packed that it's essentially pure nuclear matter. Its gravitational pull is incredible, capable of pulling in anything nearby with unbelievable force. Still, when we compare it directly to a black hole's gravity, especially supermassive ones that can rip apart entire stars in hours, neutron stars just can't compete. Some black holes can devour a whole star in less than 24 hours. Just imagine that, taking in a star like our sun, which could burn for billions of years, and tearing it apart for breakfast all before lunch. That's the kind of nightmare-level gravity we're dealing with here. In terms of raw gravitational power, the black hole takes this round, hands down. Round 2, Density. Who's really the most tightly packed monster in the universe? ***. Now here's where things get weird. You'd expect black holes to win the density contest too, right? They're the ultimate cosmic sinkholes. But believe it or not, neutron stars are actually denser. Shocking, right? Let's break this down. A neutron star crams about 1.5 times the mass of our sun into a ball just 20 kilometers across. That's like squeezing a whole mountain into a matchbox. The matter inside is so compressed that protons and electrons have been forced together to become neutrons. It's a star made almost entirely of neutrons, hence the name, neutron star ***. To put it into perspective, a teaspoon of neutron star material would weigh around 5.5 trillion kilograms. That's 5.5 times 10 superscript 1 superscript 2 kg. That kind of weight would punch straight through Earth's crust, keep going through the core and shoot out the other side without stopping. Now, black holes do have extreme mass, yes. But their event horizons can be massive, especially with supermassive black holes that sit at the center of galaxies. And when you factor in the volume that the event horizon occupies, some black holes are less dense than water. Yes, you read that right. If you count their entire size, some black holes are so spread out that they'd float in a cosmic bathtub if such a thing existed. So in terms of raw, physical density, neutron stars win this round by a landslide. The black hole may bend space-time, but the neutron star is matter at its absolute limit. It's a stellar core that's been crushed to the brink of atomic collapse. Point goes to the neutron star. Round 3, Origin Stories. Where do these monsters come from? ***. Despite how different they seem, both black holes and neutron stars are actually siblings, born from the same cosmic tragedy, the death of a massive star. When a giant star reaches the end of its life, it runs out of fuel. Without that fuel to counteract gravity, it collapses in on itself in a supernova explosion, one of the brightest, most energetic events in the entire universe. This is a star literally blowing itself apart. What happens next depends on how massive the star was before it died. If the star started off with more than about 20 to 25 times the mass of the Sun, and if the leftover core after the supernova is more than about 2.5 to 3 solar masses, then boom, you get a black hole. The core collapses beyond its limit and forms a singularity, a single point of infinite density, where the laws of physics literally break down. We don't fully understand what happens at the center of a black hole, only that it's terrifying. On the other hand, if the dying star had a mass between 8 and 25 solar masses, it might instead become a neutron star. That's assuming it shed enough of its mass during its life through stellar winds and other processes. The collapse here happens incredibly fast, in just seconds. That triggers a shockwave that blasts the outer layers of the star into space, creating that supernova. What's left is a tiny city-sized ball of pure neutrons, a neutron star. So, despite their dramatic differences in strength, size, and behavior, both these titans share the same origin story. Death by fire followed by rebirth as monsters. This round is a tie. Both of them are born from the same explosive chaos. The universe is fair that way. Round 4, range and reach. How far can their powers actually go? Asterisk asterisk. Now let's talk about how these beasts influence their surroundings. Starting with black holes, they don't just sit there quietly. They devour, yes, but they also create chaos in the regions around them. As matter spirals into a black hole, it forms a swirling disk called an accretion disk. This disk gets superheated, glowing brighter than whole galaxies. And then, if the conditions are right, black holes can launch jets of particles out from their poles at near light speed, blasting radiation across thousands of light years. These jets can affect entire galactic ecosystems, suppressing or triggering star formation in surrounding areas. It's like a cosmic gardener with a nuclear hose. Neutron stars, on the other hand, are famous for something even more bizarre: pulses of light. Some neutron stars become pulsars, cosmic lighthouses that rotate incredibly fast, blasting out beams of electromagnetic radiation with military precision. These beams sweep across space like searchlights, and if one is pointed at Earth, we see it as a pulsing signal. That's where the name pulsar comes from. And get this, some neutron stars called magnetars have magnetic fields so powerful, they could literally erase the data from every credit card on Earth from 100,000 kilometers away. That's not science fiction, that's science fact. A magnetar's magnetic field is 1 trillion times stronger than Earth's, enough to tear atoms apart. So who takes this round? Black holes affect entire galaxies. Neutron stars send out laser-like beams that can cross vast distances. But when it comes to cosmic influence and energy output, black holes still take the lead, especially the giant ones. Their reach is longer. Their influence is deeper. Point goes to the black hole. One crushes entire stars with ease. The other spins 700 times per second and blasts out beams of death. Which one wins? Today we're throwing the universe's most extreme objects into the ultimate heavyweight bout. In this corner, weighing in at 4 billion solar masses, the black hole. And in the other corner, packed into just 20 kilometers but spinning like a cosmic tornado, the neutron star. We've already covered their strengths and origin stories, but the battle is far from over. Let's push deeper into the most fascinating realms of astrophysics as we continue our cosmic showdown. Let's talk about reach, how far these cosmic monsters can stretch their influence and cause absolute chaos. When black holes feed, they don't just consume. They transform their surroundings into hellish furnaces. Matter falling into a black hole doesn't just disappear. It forms an accretion disk, a superheated whirlpool of plasma and radiation, spinning at mind-bending speeds. These disks can span light years, glowing brighter than entire galaxies, and they often produce colossal jets that shoot out from the black hole's poles at nearly the speed of light. These jets can blast through interstellar space, sending out intense waves of radiation, frying anything unlucky enough to be nearby. And then there's spaghettification. Yes, it's as terrifying as it sounds. As you approach a black hole, the difference in gravitational pull between your head and your feet becomes so extreme that your body would be stretched into a thin strand of atoms. Imagine being squeezed and pulled into an infinite noodle of yourself, all because the black hole's tidal forces are so incredibly intense. If that doesn't define extreme destruction, nothing does. But don't count neutron stars out just yet. These little monsters might be smaller, but they have their own way of creating universal mayhem. When two neutron stars collide, an event known as a kilonova, the resulting explosion is even more dramatic than a supernova. For a brief moment, these collisions create conditions hotter than the center of any known star. This violent interaction doesn't just blast matter into space, it forges the heaviest elements in the universe like gold, platinum, and uranium. That ring on your finger? You can thank a neutron star collision for that. These collisions also send gravitational waves rippling across the universe, tiny distortions in spacetime that we can detect right here on Earth. That's right, when neutron stars crash, the entire universe shakes. And these waves help scientists unlock the secrets of dark energy, black hole formation, and the true nature of gravity itself. While neutron stars don't have the long-reaching influence of black holes, their bursts of chaos are potent, localized, and scientifically invaluable. Still, if we're talking about reach in the literal sense, black holes win this round. Their gravitational grasp extends far beyond what a neutron star can achieve. Supermassive black holes at the centers of galaxies don't just sit there. They actively sculpt the formation of entire star systems, influence galactic structure, and sometimes even stop new stars from forming by heating up the surrounding matter so much that it can't cool down and collapse into stars. That kind of power is not just terrifying, it's godlike. Let's bring this battle a little closer to home. As of 2024, the nearest known black hole to Earth is about 1,500 light-years away. That sounds far, but in cosmic terms it's practically our neighbor. The closest neutron star? Roughly 400 light-years away. That might sound scarier, but don't panic. Neither of these cosmic beasts is heading in our direction anytime soon. Still, it's humbling to realize that such unimaginable forces exist relatively close by. Now let's dive into one of the neutron star's most bizarre talents, its ability to become a pulsar. Imagine a cosmic lighthouse beaming out jets of radiation while spinning hundreds of times per second. The fastest known pulsar spins 716 times per second. That means its surface is moving at about 15% the speed of light. If Earth rotated that fast, we'd be vaporized in a second. Pulsars emit steady radio waves, X-rays, or even gamma rays, and thanks to their precision, they serve as the universe's most accurate clocks. That's not an exaggeration. Pulsars are so stable in their rotation that scientists use them to track time in deep space more precisely than our most advanced atomic clocks. They've become vital tools in interstellar navigation and studying the laws of physics under extreme conditions. Imagine that, a dead star no bigger than a city helping humanity explore the cosmos. And then we have magnetars, the neutron stars on steroids. These are the most magnetic objects in the universe, with magnetic fields quadrillions of times stronger than Earth's. If a magnetar passed within a few hundred kilometers of our planet, its magnetic field could distort atoms and fry all electronic devices. It's hard to overstate how intense this is. Magnetars can even crack their own crusts, releasing massive bursts of energy that we can detect across the galaxy. Black holes, on the other hand, don't offer this kind of variety. They have one job: consume. Sure, they warp space and time to a degree that defies logic. They can trap light, twist time into knots, and maybe even lead to other dimensions if you believe some speculative theories. But beyond that, black holes are surprisingly quiet. They don't emit light, they don't pulsate or rotate in ways we can measure easily, and unless they're actively feeding, they're nearly invisible. So if we're awarding points for weirdness and versatility, this round clearly belongs to neutron stars. They behave in ways that stretch the limits of what we understand about physics. They're tiny but fierce, mysterious but measurable, and chaotic but reliable. It's hard not to admire that kind of paradox. So, after all the epic battles, who wins? The score is tied. Black holes dominated in gravity and reach, with a level of destructive capability that spans light years. Neutron stars conquered in density and bizarre behavior, surprising us with their versatility and value to science. Their formation stories, though different in outcome, start from the same place: the fiery death of massive stars. But maybe this showdown isn't really about winners and losers. Maybe the point is to marvel at how the universe can create such diverse monsters out of the same raw material. Maybe it's about understanding how extremes in nature help us grasp the limits of what's possible. Black holes and neutron stars aren't just science fiction villains. They are cosmic laboratories, teaching us about the nature of matter, energy, time, and even the origins of the universe. And if this epic clash has sparked your curiosity, you're not alone. Humanity is just beginning to understand these titans of the cosmos. With new telescopes like the James Webb Space Telescope and advanced gravitational wave detectors coming online, we're on the verge of discovering even more about these enigmatic objects. Who knows what mysteries still lie hidden in their depths?